Calculus video 36, derivatives of logarithms with base e. So now we have logarithms. We're going to only at this point talk about logarithms of base e and the derivative of logarithms with base e, and then in the next video we'll move into logarithms with other bases. That's not just base e. So if you recall, a function y equals log base e of x, we use it so often we call it the natural log of x, the natural log function. We give it its own notation called the ln of x. And so we have y equals ln of x being the same thing as y equals log base e of x. Right, so if you see an ln of x, you have to know that is log base e. The graph is the inverse of the exponential function e to the x. So this curve here is y equals the natural log of x. It has a vertical asymptote at x equals 0. It gets close to that vertical asymptote as it goes down to negative infinity. The natural log of 1 is 0, and then it curves off to the right there as like an inverse of that exponential function. Right? That exponential growth that you're used to seeing with exponential functions, that's the same rate that you're getting with the logarithmic function growing then to the right. Question is, what is the derivative of the natural log of x? Right, our goal is to find, say, any point on the y equals natural log of x and be able to find the slope of the tangent line. Keep missing my drawing here. That's close enough. All right, what is this slope? To find the slope, we'll do the derivative, right? So we have to know the derivative of the natural log of x. So let's, without further ado, have a nice proof here. So proof to see that the derivative of the natural log of x is 1 over x. Okay? Seems like a good, nice, solid answer here. To get there, let's start with this. Let's let y equals the natural log of x. But we know that means that y equals log base e of x. Right? That those natural log of x, log base e of x, same thing. Now what I want to do is, instead of taking the derivative of this form, I want to first turn it into exponential form. You might be asking, why are we turning it into exponential form? Well, the answer is we know how to take the derivatives of exponents. That's the video we just did previously. And so if we can turn it from logarithmic to exponential, take the derivative in exponential form, and then turn it back, we can find the derivative of the logarithm. So to turn a logarithm into exponential form, what you do is you take the base of the logarithm, in this case e, raised to the power of the answer, y, is equal to what you were taking the logarithm of, in this case, x. So y equals log base e of the x is the same thing as e to the y equals x. That's the exponential form of that logarithm. Okay, so the derivative of y with respect to x, dy dx, that's the derivative of the logarithm, natural log of x. Let's just think about it like this, right? So if I want the derivative of y, if I want dy dx, that is the derivative of the natural log of x. That's what I'm looking for. So if I can solve for dy dx, I will have my answer. But I want to do it using this form here. So we're going to start with e to the y equals x, and we're going to take the derivative implicitly. Why don't you try it? Try taking the derivative implicitly here and see what you get. Remember, implicit differentiation is whenever you take the derivative of a term with a y in it, you need to multiply it by dy dx, but a derivative of a term with just x is just its derivative. Okay, so taking the derivative implicitly on both sides here, the derivative of e to the y, it's an exponential function, so its derivative is itself, e to the y, times the chain rule, the derivative of y, so times dy dx. And we'd also do it times the natural log of the base, except for it's just base e, so you don't have to. And the reason you don't have to is because the natural log of e is 1, and so you're just like multiplying by 1 here. All right, so that's the derivative implicitly on the left-hand side. The derivative implicitly on the right-hand side, the derivative of x is 1. Solve for dy dx. Solving for dy dx, we get dy dx is 1 over e to the y. And up here we see that e to the y is equal to x, so I can replace e to the y with x. And we get that the derivative of y with respect to x is 1 over x. The derivative of y with respect to x is the same thing as saying the derivative of the natural log of x. So we have thus proven that the derivative of the natural log of x is indeed 1 over x. Okay, that's nice. Nice proof there. Pretty short. Let's go ahead and write this out kind of properly. We have the derivative of logarithms base e. Derivative of logarithms base e. The derivative of the natural log of x is equal to 1 over x. However, if that function is not just x, what if you have the derivative of the natural log of u? Right, it's not just an x there, but it's a 2x squared minus 5x, or a sine x, or a tangent of x, right? That u is some function of x. Then your answer is not just 1 over x, but 1 over whatever that function is, u. And the chain rule says we then have to multiply that by u prime. And often we write it like this. The derivative of the natural log of u is equal to, instead of 1 over u times u prime, we can take that u prime in the numerator and think about that as u prime over u. And that's typically the way we think about the derivative of the natural log of u, is u prime over u. Okay, let's try that. Let's use this one here, this derivative of the natural log of u is u prime over u, with, I think I have about 5 different examples. So 1, what is the derivative of the natural log of 4x plus 5? Okay, pause the video, see what you get. All right, so the u here is the 4x plus 5. So the derivative is u prime over u, the derivative of u divided by the thing u. It's like, remember, we're thinking of it like 1 over u times its derivative. That's the chain rule. But just for convention, we typically do u prime over u. The derivative of 4x plus 5 is just 4 over whatever u was, in this case 4x plus 5. We cannot cancel the 4's there because the denominator 4 is 4x plus 5. It's being added or subtracted to something else. So that's our answer, 4 over 4x plus 5. U prime over u. All right, number 2. What is the derivative of x squared minus 6x plus 1? Sorry. The derivative of the natural log of x squared minus 6x plus 1. Again, we're thinking u prime over u here. The derivative of x squared minus 6x plus 1 is 2x minus 6 over u, which is x squared minus 6x plus 1. The numerator will both divide by 2, but not every term in the denominator will. I think that's going to be it as an answer. 2x minus 6 over x squared minus 6x plus 1. U prime over u. All right, number 3. A little bit harder now. Let's do the derivative of the natural log of x squared times sine x. Okay. The reason this one is more difficult is because the inside function is x squared times sine of x. That's 2 functions multiplied, so we're thinking, oh, I'm going to have to use a product rule here. And you could, but that would be the more difficult way to get this answer. Quite a bit more difficult. Instead, before you do the u prime over u, before taking the derivative, big star by this is important, before taking the derivative, use the properties of logarithms to separate this into multiple logarithms. Before taking the derivative, use the properties of logarithms to separate into multiple logarithms. And we do that because we have two functions multiplied by each other inside the logarithm. Right? Two functions. Anytime you have two functions multiplied by each other inside the logarithm, you want to separate them first. Actually, if you have three functions multiplied inside the logarithm, or four functions multiplied inside the logarithm, you want to separate them into their own logarithms. Or, if you have a function divided by a function inside the logarithm, or two functions divided by three functions inside the logarithm, you want to separate them all into their own little logarithm prior to taking the derivative. Right, it should look something like this. It'll make your life a lot better doing it this way. Instead of the derivative of this, we're going to look at this as property of logarithms. And the property we're using here is, let me back up. The property is the log base a of m times n is the log base a of m plus log base a of n. If you have two things, m times n, two functions multiplied inside of a logarithm, you can write them as two separate logarithms added, right? Or more, well, we'll get to more generally in a second. In this case, when we have the derivative of the natural log of x squared sine of x, we're going to rewrite this as, not derivative yet, just going to rewrite the natural log of x squared plus the natural log sine of x. We're going to separate that and write it as two different logarithms added together. And then, one more thing. Before you take the derivative, any term with a exponent on it, like we have a x squared here, this 2 here, can come out in front of its own logarithm. Not in front of the whole derivative, but just in front of its own logarithm. So one more simplification here. This is equal to the derivative of 2 natural log of x plus the natural log of sine of x. Now let's take the derivative. We get 2 times. What's the derivative of the natural log of x? 1 over x. Plus, natural log of sine of x. Sine of x is like the u function. So that's u prime over u. What's the derivative of sine of x? Cosine of x over itself, the sine of x. Our answer here is 2 over x plus cosine of x over sine of x. Or if you like to use trig functions, cosine over sine is cotangent. This is 2 over x plus the cotangent of x. And I promise if you did it the original way with the product rule, it would not turn out this nicely or be this quick. So, once again, anytime inside of a logarithm you're taking the derivative and you have more than one function multiplied or divided there, not added or subtracted, but multiplied or divided, you want to separate them out into their own logarithm before taking the derivative. And also, any exponents, like this natural log of x squared, can come out in front of its own logarithm before taking the derivative. All right, let's try at least one more here. Number 4. The derivative of the natural log of 5x times the square root of x squared minus 1 divided by the cubed root of 3x plus 4. Now this would be an exceptionally hard problem if you did just u prime over u here. Picture u prime. When doing the derivative of the inside, it's a quotient rule and a product rule in the numerator of the quotient rule. That would be exceptionally complex. So please don't do that. That will take up the whole page and your whole test time. Instead, we're going to rewrite first. Rewrite first. Exclamation points. Okay, we're going to separate this into, I see 3 logarithms. I see a 5x up here. That's a term. I see this square root of x squared minus 1. That's a term. And I see this cubed root of 3x plus 4. That's a term. 3 terms. Now, 2 of the terms are in the numerator. In fact, maybe I'll color code these things. 2 of the terms are in the numerator, 1 term in the denominator. Any term in the numerator has a positive logarithm. Any term in the denominator has a negative logarithm. So let's rewrite derivative. We haven't taken the derivative yet. The derivative of the natural log of 5x. Positive natural log here because the 5x is from the numerator. Plus the natural log of square root of x squared minus 1. I don't think I'll write it like that. I think I'll write it as the natural log of x squared minus 1 to the 1/2 power. Square root is the 1/2 power there. And then minus, make sure you put minus for this one, the natural log of 3x plus 4 to the 1/3 power. Okay, now you could take the derivative right now, but it will be even easier if you'll first take any power here, this 1/2 power and this 1/3 power, and bring them using properties of logarithms out in front of their own logarithm. This will save you a lot of work. So we have the derivative of natural log of 5x, which, by the way, we could actually make this two separate logarithms, the natural log of 5 plus the natural log of x, if you want to. Could do that, but I'm not going to. Plus 1/2 natural log x squared minus 1. Now there's no exponent on that x squared minus 1, makes it a lot easier. Minus 1/3 natural log 3x plus 4. Okay, so I've got, in this first one, my u is 5x. In the second one, my u is x squared minus 1. And in the third one, my u is 3x plus 4. So in each case, when I do the derivative now, it's going to be u prime over u, right? For everyone, u prime over u, u prime over u. The derivative of u, so 5x, its derivative is 5 over 5x. Plus, the 1/2 is just going to hang out front, and then it's u prime over u. X squared minus 1, its derivative is 2x over x squared minus 1, u prime over u. Minus 1/3, 3x plus 4, the derivative is 3 over 3x plus 4, u prime over u. If you want to think about those in parentheses there. Okay, let's see if we can simplify. I see the 5 over 5 cancel out, and that is just 1 over x then. Plus, I see a 2 and 2 cancel out, so that is x over x squared minus 1. Minus. 3 and 3 cancel out. That won't always happen. That's kind of a special case here. Minus 1 over 3x plus 4. And feel free to leave it in this form without having to combine those fractions. Just leave it 3 separate fractions. All right, so that is how we will take the derivative of this monster here by first rewriting, second bringing the exponents out in front of the logarithm, and then take the derivative of each logarithm u prime over u. Let's go ahead and try a couple more. Let's try some hard ones. Let's try, if we have a function y equals the square root of 3 natural log of the tangent of x. 3 natural log tangent of x. All right, that looks like a power rule to me. Let's do this. Let's 3 natural log tan x raised to the 1/2 power. So it's a power rule, but 1/2 power, but it's also chain rule. And it looks to me like a chain rule inside of a chain rule, with the outside function being to the something to the 1/2 power. Then the inside, kind of middle inside function is then 3 natural log of something. And then the inside function is tangent of x. So let's try our derivative here, y prime. We'll bring the 1/2 out of whatever is on the inside, now to the negative 1/2 power. Okay, times the derivative of the inside. So this is kind of that middle inside. The derivative of 3 natural log tangent of x. Well, that's 3 times the natural log. So the derivative of natural log is u prime over u prime. The derivative of tangent of x is secant squared of x over tan x. And so we already got that sort of inside derivative by doing the derivative of tangent of x here being secant squared of x. So that's just it. Let's see. If I rewrote this, that would be 3 secant squared of x over 2 tan x times the square root 3 natural log tan x. Something like that. And there's probably some cancellation here with the secant squared being 1 over cosine squared, the tangent being sine over cosine. One of those cosines could probably cancel, but I think we'll call it good there. Let's try one more. How about y equals 4 to the power of natural log of x squared plus 5? All right, what is the derivative? Again, try it at home. Pause the video and then see what you get afterwards. I've got y prime is equal to the derivative of 4 to some power. It's an exponential function, therefore it's always just itself, times the derivative of the exponent. All right, so the inside part here is natural log of x squared plus 5. Its derivative of the natural log is u prime over u. So we're going to replace u prime over u with the derivative of x squared plus 5, that's 2x, over x squared plus 5. And then, easy to forget, we have an exponential function, but that base is not e, right? And if the base is not e, you then have to multiply this thing by the natural log of the base. And that's basically all we can do here. We'll just go ahead and leave it as such. All right, so that would be, going back up here to our sort of summary, the derivative of natural log base e, or logarithms base e, the derivative of natural log of x is 1 over x. But if you have something besides just an x there, if it's some other function, as complex as it might be, we have the derivative of the natural log of u is u prime over u. Remembering, if we have multiple functions inside that logarithm, to separate those functions before taking the derivative.